too. Um, yeah, uh, that's really great. Thanks so much. Let's move to our second speaker, Niklas. He's going to tell us about expressivity for GNNs and why maybe the WL test isn't going to like cut it long term. That's my short version summary, but you can take it from here.
Thanks for the introduction. Uh, you can see my screen, right?
Yes, looks very good.
Okay, perfect. Yeah, I'm going to present our paper on the limitations of classical expressivity theory and what we can do about it, and how we developed sort of a complexity measure. And this was joint work with my amazing colleague Tom and my supervisor Stephan. And I'm sure you've all seen the following two graphs. And you also already probably know that they cannot be distinguished by standard GNNs. And in theory, this seemed like a really big problem. And once this fact was known, the hunt for more and more expressive architectures basically began. And now we have like a plethora of more expressive higher order or substructure biased or topologically inspired architectures. And correspondingly, with this increase in architectures, we also saw an increase in expressivity measures that basically, or most of them were some variant of the Weisfeller-Lehman test. And I myself also worked on this, like in a previous project. And in theory, we can demonstrate greater capabilities with these new expressivity measures for our new architectures. But if we look at the practical side, it's not really clear if what we see above is actually a problem. Oh, sorry. In many real-world applications, still standard GNNs are used, and rarely higher order or more expressive GNNs are actually used real-world application. Additionally, a recent paper showed that standard GNNs, like a GCN with a few tweaks, actually achieves comparable or even better results to more expressive architectures in almost all popular benchmarks. So on the one hand, we have the theory side where we show greater capabilities, but in practice, this doesn't really translate to better results. So what goes wrong here? Why do we have this gap? To answer this, we first need to understand what we mean by expressivity theory here. And in our work, we focus on the predominant framework isomorphism-based expressivity theory. And basically what we are doing here is we characterize the ability of our model class to distinguish non-isomorphic graphs relative to a graph isomorphism test, which could be a variant of the Weisfeller-Lehman test. And if there exists some model in our model class that can distinguish at least those graphs that the isomorphism test can distinguish, then we say it is at least as expressive. So what are potential problems here that show that high expressivity doesn't imply good empirical performance? The first problem, or the first limitation, is that this characterization is completely binary. So a model can or cannot distinguish two graphs, and we have no notion of difficulty here. It's just binary. And something that's theoretically feasible can, as we all know, be exceedingly hard to learn and practice. And we lose this information, or we abstract away from this information isomorphism-based expressivity theory. And secondly, we are only making existence claims here. We are only claiming that, or we are only showing that there exists some model in our model class that can distinguish those graphs. And typically proofs use a completely idealized model that has like perfect information flow where one node receives all the information from all other nodes in the graph. We don't have oversquashing, we don't have underreaching. We have perfect update functions and so on in our proofs, but in practice, we don't have this. And these 2 points already show why high expressivity doesn't necessarily lead to good performance. Let's look at the other side, why low expressivity also doesn't necessarily constitute a limitation for standard GNNs. First of all, in isomorphism-based expressivity, we focus only on a single task, namely distinguishing non-isomorphic graphs. And it's not clear if this is like the most important task in domains like social network analysis or relational deep learning. We might only care about efficiently aggregating local information, and we don't really care about if the model is able to distinguish non-isomorphic graphs. So this focus on the hardest possible task, distinguishing non-isomorphic graphs, is maybe wrong or is not aligned with the practical needs that we need in the real world. Additionally, we are making global worst case statements. So a single counterexample that we cannot distinguish is sufficient that we say that the model is not at least as expressive as alpha. And these counterexamples are really rare in practice. If you take random graphs, the probability that they cannot be distinguished by the basic Weisfeld-Lehmann test is or approaches zero. And if you look at popular benchmarks, 99.99% of all graphs can be distinguished. And lastly, we are always making statements about the set of all possible graphs. But in reality, if we look at concrete applications, we often have like restricted sets of graphs. For molecules, maybe planar graphs with bounded degree and so on, where our model might perform better. So this together shows the divide between expressivity and practical performance. Now, let's try to overcome this divide and overcome these limitations. And for this, we tried to develop a complexity measure. And we need to take a few steps until I can define it. And the first step is we don't want to make worst case statements about tasks and graphs. We want to look at individual tasks and individual graphs. And for this, we need the following definition. I won't go into too much detail here, but basically, this notion here in the middle means that a function h contains all the necessary information so that we can deduce the output of the function f of g. So you can imagine that h of g is more fine-grained, or at least as fine-grained as f of g, and contains all the relevant information. And this will later allow us to make like local statements about individual graphs instead of just worst case statements about sets of graphs. And the second step that we need to take is that we somehow need a way to account for practical limitations. And what we identified as the most important practical limitation is that message passing in practice is lossy. We don't have this idealized model that can aggregate information from all over the graph, but we have effects like over-squashing, over-smoothing, limited depth, so underreaching, and so on and so on. And how can we theoretically model this? And the idea for this is, okay, then maybe let's have something like a probabilistic Weisfeld-Lehmann test in which messages can be actually lost. And our theoretical model then independently loses messages with some probability, and our Weisfeld-Lehmann color now is not deterministic anymore, but a random variable. And this theoretical framework should basically capture this lossiness of message passing. And now we can put everything together and define our message passing complexity. And basically, it depends on the probability that some task F on a graph G can be solved under lossy message passing. So imagine a task requiring information from many distant nodes. Then the probability that lossy Weisfeld-Lehmann will contain all the information to deduce the task output will be very low, and correspondingly, the complexity will be very high, which is reasonable because this task is difficult because it requires a lot of information flow. On the other hand, if we have a task that requires only information from very near local neighbors, then the probability that lossy Weisfeld-Lehmann still contains like all the information that is needed to deduce our task F will be very close to 1, and our complexity will be correspondingly near zero. And this is the formulation for standard GNNs, but we can also like generalize it to many other higher order GNNs by basically adapting this lossy Weisfeld-Lehmann test. And let's compare to like isomorphism-based expressivity theory. Now we have a continuous complexity measure, which continuously characterizes difficulty. We explicitly account for practical limitation in the sense of this lossy information propagation, modeled through the lossy Weisfeld-Lehmann test. And importantly, we can characterize complexity for any task. So our complexity measure depends on the task F, and we don't only look at the worst case task of distinguishing non-isomorphic graphs. We have now a local measure which depends on the individual graph, and we can say, okay, for this graph it works, for this graph it works, for this graph it doesn't work anymore. And additionally, this also allows us to make statements about real graphs, basically, about sets of real graphs. Okay, and let's look a bit at the theory behind MPC. What we theoretically can show is that message passing complexity subsumes isoexpressivity theory, because we can show that the tasks for which complexity is infinite are those that are unsolvable with an MPNN on G, and the tasks for which the complexity is finite are those that are solvable. And by choosing now an isomorphism test as our task F, we can basically recover like this binary possible, non-possible distinction of isoexpressivity theory. And then additionally, we can show that MPC is explicitly connected to oversquashing. If a task requires information flow from one node U to another node V, then the complexity measure is connected, or the complexity value is connected to the random walk probability from V to U, which has been shown to be a measure of oversquashing. Okay. And lastly, let's look at the empirical performance. And generally, we see a good correlation between performance and MPC on the fundamental tasks we tested. The fundamental tasks are like retaining information, propagating information, and extracting topological information, so finding something like a ring. And importantly, the optimal architecture for all these different tasks that we tested depends on the task. So a global characterization of expressivity of models, like used in isomorphism expressivity theory, cannot capture that performance varies from task to task. And the best model is not necessarily the model with the highest expressivity. Instead, our task-specific complexity measure, which sort of measures how well the inductive bias of the model is aligned to what the task actually requires, is more predictive. In summary, we present message passing complexity, and we have seen that message passing complexity narrows the gap between theory and practice by overcoming the mentioned limitations. But I want to be crystal clear, there's still a huge gap between theory and practice, and we cannot completely capture empirical performance. And so a lot of huge research is needed to discover more practically meaningful limitations and then integrating them into theory so that we can theoretically reason about them. And that's it from my side. And now I'm looking forward to the questions and also seeing you in San Diego if you happen to be there.